Assalamualaikum warahmatullahi wabarakatuh. Hi and good day to everyone. Today I would like to introduce you guys to our topic, which is application of definition. So before we begin, I would like to introduce to you guys our project members. So here we go.
First of all, we would like to thanks to our lecturer, Sir Anas Fatul bin Arifin, for guiding us until we managed to complete with this video presentation successfully. Beside that, we would like to thanks our group members for being cooperative and helpful during completing this video. Because without these great teammates, this video will become impossible to complete. We are also grateful to our lecturer of calculus, Sir Anas, for teaching us this subject and willing to help us to fix our lacking knowledge about this subject. Lastly, we appreciate and would like to express our gratitude to our friends and also family for motivation and encouraging us all the time. May these memories stay forever. So, the topic we will discuss with everyone is rate of change, which is the subtopic related rate.
Introduction. One of the application of differentiation in calculus. It is involving us to figure out a rate of changing of a quantity from another quantity that is given. The rate of change of a quantity refers to how that quantity changes over time. Rate of change are commonly used, especially in applications of motion. Typically, the rate of change is given as a derivative with respect to time and is equal to the slope of a function at a given point. The rate of change of a function varies along a curve, and it is found by taking the first derivative of a function. The derivative of a function yx is the rate of change of that function at point x, yx. The rate of change at a specific point is known as the instantaneous rate of change.
So, moving on to the problem statement. A 30 feet long ladder rests against a house on a flat ground. The bottom is initially 8 feet long away from the house wall. The ladder is moving up when it is being pushed towards the wall at the rate of 1/5 feet per second. Calculate how fast the top of the ladder moving up the wall 15 seconds after we start pushing.
For the first step, we can draw the figure that you understand from the question and label the data given that related to it. From the problem statement, we know that the bottom of the ladder is 8 feet away from the house wall. We also know that the ladder is moving up at the rate of 1/5 feet per second. Based on this question, it asks us how fast the top of the ladder is moving up, which is dy/dt. So, from the information given, we know that x/dt is 1/5 feet per second, and the question asks us to find dy/dt.
Figure given using the theorem Pythagoras method. As we all know, theorem Pythagoras is a square plus b square equals to c square. So, by substituting the figure, you will get y square plus x square equals to 30 square. So you have to differentiate all of this using the implicit method, and then you will get 2y times dy/dt plus 2x equals to 0. Okay, initially, the bottom of the ladder is 8 feet from wall. At 15 second distance is equals to rate times time. As we all know, rate is 1/5 feet per second. Times with 15 second, that is time, you will get 3 feet. So, the initial distance will minus it with the new distance, and then you will get 8 minus 3 equals to 5 feet.
Next, since we already know the value of x, which is 5, we can find the value of y. We can use the Pythagoras theorem once again here in order to find the value of y. Substitute all of the known value into the Pythagoras theorem formula, and we will get y equal to square root 875.
Now we're moving on to the step 4. In this step, we need to 2y multiple dy over dt plus 2x multiple dt dx over dt equal to 0. Then 2 square root 875 multiple with dy over dt plus 2 multiple with 5 multiple with negative 1 over 5 equal to 0. So 2 square root 875 multiple with dy over dt equal to 2. And the final step is dy over dt equal to 2. Divide with 2 square root 875 and we will get the final answer is 0.0338 feet per second. So that's all from us. Thank you for listening.